Inside a soundproof booth sits an art installation called Echo. It's a smart AI mirror, but it does not process the meaning of your words. Instead, it listens exclusively to your prosody, the tone, rhythm, and attitude of your voice. This operates on what we can call the principle of asemantic reflection. Childhood psychology, Jacques Lacan described the mirror stage, the moment an infant recognizes their external reflection, triggering an awareness of their own autonomous ego. Echo weaponizes this concept. By interacting with an algorithm that perfectly mimics their tone, users are forced to observe the attitudes they usually conceal. The machine strips away the polite definitions of their words, leaving only a raw reflection of their disposition. The installation proves a subtle point. When humans interact with an artificial intelligence, they are rarely engaging in a purely objective exchange of data. They are participating in a psychological reflection. This psychological mirror is currently being built into the most critical bottleneck in software engineering, the human-in-the-loop data annotation pipeline. Machine learning relies on immense datasets curated by human evaluators to establish ground truth. Yet, despite massive financial investment and rigorous mathematical structures, these pipelines consistently produce systematically biased training data. To understand why, researchers from LMU Munich and the University of Maryland conducted an experiment with nearly 2,800 participants. They adapted a survey methodology framework called dependent verification to isolate the variables of AI evaluation. The results isolate a highly specific failure state. In workflows where humans review AI-generated labels, known as pre-annotations, the evaluators routinely overwrite objective reality with their own psychological assumptions. Debugging an algorithmic hallucination is a math problem, but fixing the foundational models of tomorrow requires measuring and mitigating the hidden cognitive attitudes of the human pulling the strings. This screen displays the exact task the LMU researchers built. Participants were given financial tables and asked to extract corporate greenhouse gas emissions data. The parameters were absolute. There was an objective true label for every instance, governed by strict reporting rules. The researchers deployed a Wizard of Oz setup. The pre-annotations were framed as AI-generated, but were actually manually controlled by the researchers to inject specific errors and interface conditions into the workflow. We can plot the annotator performance on a confusion matrix. The two metrics that dictate system failure are overcorrection, changing a correct AI suggestion into a wrong one, and undercorrection, leaving an incorrect AI suggestion marked as right. The first variable the researchers tested was Principle 1 of dependent verification, the human drive to reduce cognitive working capacity. They introduced microscopic friction into the user interface. For a specific subgroup, if they classified the AI suggestion as incorrect, they could not just click a button. They were forced to manually type the correct value into a text box. The behavioral shift was immediate. Forcing humans to exert the minor effort of typing a correction caused a significant, measurable drop in the total number of corrections made. This friction triggered a dangerous side effect. As overall corrections dropped, the researchers recorded a massive spike in the undercorrection rate. Participants unconsciously adapted to the interface constraint. To save themselves the mental and physical effort of typing, they simply underreported the errors the AI was making. A minor design choice created acute automation bias. By slightly increasing the workload of disagreeing with the machine, the interface turned objective evaluators into rubber stamps for AI hallucinations. The data labeling industry assumes you can eliminate this cognitive shortcutting by paying for precision. They rely heavily on performance-based pay. These two side-by-side line charts plot the accuracy of annotators motivated by a top 10% financial bonus against a control group. The lines are identical. The financial incentive had zero statistical impact on human accuracy or effort.
The researchers then tested the anchor fallacy, the assumption that seeing an AI fail repeatedly early on destroys user trust. The data disproves this entirely. Exposing a group to 3 consecutive initial AI errors produced another absolute flatline, not changing their subsequent evaluation accuracy. Financial incentives failed, initial impressions failed, but there was one variable that practically guaranteed human failure: conceptual complexity. Look at this chart measuring average accuracy by error type. When the AI made a simple spelling error, humans caught it 82% of the time. But when the error required understanding complex concepts, like the difference between Scope 1 and Scope 2 emissions, accuracy plummeted to 31%. Neither the promise of extra money nor a bad first impression can override our cognitive limits. When a problem becomes conceptually difficult, humans default to relying on the algorithm. To find what actually drives beta quality, the researchers relied on a 6-item attitude scale survey administered to the participants a full week before the data extraction task. This survey sorted the participants into 2 opposing cohorts based on their general feelings toward automation: the AI skeptics in the lower quartiles and the AI enthusiasts in the upper quartiles. The survey predicted the outcome of the experiment. The AI skeptics systematically built better, more accurate ground truth data than the AI enthusiasts. Because they lacked inherent trust in the machine, the skeptics scrutinized the pre-annotations thoroughly. They reliably detected errors and maintained high accuracy across the entire task sequence. The AI enthusiasts exhibited the exact opposite behavior. Their favorable view of automation led to extreme over-reliance, blind trust, and a dangerously high rate of undercorrection. It is easy to assume this variance is simply correlated with standard demographic factors, that age, sex, or ethnicity might be driving the split. This coefficient plot isolates the variables. After controlling for all other factors, an internal attitude toward automation emerges as a stronger, more significant predictor of success than any demographic marker. The extraction task was purely mathematical. The answers were objectively right or wrong, yet the outcome was hijacked by subjective bias. In human-in-the-loop workflows, the evaluator's pre-existing psychological attitude acts as an override switch. It is the ultimate bottleneck for data quality. The LMU data suggests that ECHO's core mechanic, the reflection of human attitude, is a constant presence in technical workflows. Humans do not treat algorithms as objective tools. We project our internal attitudes onto them, treating the output as a subjective psychological mirror. When this cognitive dynamic is left unchecked in enterprise machine learning pipelines, it triggers the cascade effect. The enthusiast-driven undercorrections stop being seen as human mistakes. Once they pass through the interface, they are permanently embedded in the database as absolute, verified ground truth. These embedded, human-approved AI hallucinations are then used to update the weights of the next generation of foundational models. This creates a recursive cycle. The models generate flawed data, humans cognitively shortcut the review process and approve it, and the model learns to be more confident in its errors. It is nearly impossible to debug later. Ignoring annotator psychology degrades the mathematical integrity of future models, embedding human bias into the foundation of the system. Systems architects must begin engineering around human psychology, rather than assuming human rationality. The first structural solution is to decouple judgment from correction in the user interface. If you separate the act of flagging an error from the burden of typing the correction, you eliminate the friction-induced undercorrection bias. One group judges, a separate group corrects. The second solution is implementation. Attitude measurement protocols, like the 6-item scale used in the study, must become a mandatory step before cohort selection. A functional human-AI pipeline requires meticulous accounting for the psychological reflection of the human pulling the strings, alongside algorithmic optimization.